Okay. Before continuing our discussion, let me tell you that the lesson of next Friday, so please take note, is now suppressed since I have to go for the second vaccine dose. So next Friday, we at midnight, 12, we will not meet for our lesson. Having said that, we were discussing about physical vapor deposition. Here you have listed the most common, apart from the possibilities they exist, of materials which are used in physical vapor deposition for the application which are interesting for us in our course. That means wear and resistant coatings. As you can see, we have essentially non-oxide materials, and they can be divided into monolayer coatings or multi-layer coatings. For the monolayer coatings, we have most of time nitrides, or in some cases carbides, relying on binary compounds. We can have also the possibility to fabricate ternary compound coatings like those listed. Essentially, most of times they are nitride bases, and they can be also fabricated by reactive physical vapor deposition methods. For the multi-layer coatings, more than one layer, more than two layers, usually the combination, they see nitrides or carbon nitrides, and the choice of these materials is strictly linked to the high hardness that we can obtain on the surface of the treated component by using this kind of materials, this kind of coatings. And so some existing very common examples, they are cutting tools, for example, in which hardness is very important because it affects directly the lifetime of the tools. One common is this one, in where you see a yellow coating. Titanium nitrides is yellow, and so when you see a yellow PVD coatings, essentially it is based on titanium nitride. Also in automotive components, this kind of wear-resistant coatings are used. For example, titanium nitrides for wheel or camshaft, or chromium nitrides for con rod, just to give you an example, or piston rings. And this is instead an example of what we mentioned of super-lattice coatings, that is multi-layered coatings having the single layer in a nanometer range in terms of thickness, even though the total thickness, as you can see here, is as usual of some micrometers, and they are fabricated with a PVD system reactive based essentially on sputtering. And again, these are proposed to be used for what it concerns camshaft or whales, for example, or for tools which are used in the fabrication or plastic deformation of metallic alloys. If we move to the second block, to the second class of vapor-based methods for coating fabrication, we already said that we have the so-called area of the chemical vapor deposition technologies. This area of technologies is different from the physical vapor deposition technologies because by using techniques which are classified under CVD head, we deposit our film, we fabricate our coating by relying on the existence of a chemical reaction and surface absorption. So we introduce reactive gases into the chamber where the coating is going to be fabricated. We then need to activate the chemical reaction. That means we need to activate the precursors, the gases, typically gases. It could be also the composition reaction, not necessarily a chemical reaction. And this activation requires energy. And the energy is given in the form of heat or by using a plasma. Thus, we have the mechanism of the gas absorption by the substrate surface, which must be coated. And in this way, the chemical reaction or eventually the decomposition take place on the surface and the coating is going to be fabricated. We do have always exhaust waste during this chemical reaction, which must be evacuated from the chamber, and they are usually in the form of resulting gases. So the chemical vapor deposition involves the dissociation and or a chemical reaction of reactants, which must be activated, heat, light, plasma, and with the formation of a stable solid product. So the typical case is that in which we do have two gaseous reactants. They react chemically, they are activated, and one of the products of the chemical reaction is a solid. This solid, being the gases absorbed onto the surface, give rise to the coating that we want to fabricate. So we need, in order to have a good coating, homogeneous gas-phase reactions or heterogeneous chemical reaction, depending on which they are going to happen. And here you have some example of coatings, then there will be more detailed examples, which are related to the fabrication of nitrides or carbon nitrides. And you see, if you look these figures, we are going to move to deposition rates in terms of micron per hour, which are higher than those which basically characterize the PVD process. That's the scheme. So we do have the reactive gases. They are absorbed onto the surface of the substrate. The chemical reaction is going to happen. We do have an exhaust product, which is typically in the gaseous form, which must be evacuated from the chamber itself. Just have a look to some possible CVD reactions. In the case, for example, of oxidation, that is a formation of oxide solids, generally speaking, we can have, generally speaking, the precursors, which could be gas or solid. Then we have for oxidation, the second component, which is most of the time oxygen, if we want to need oxides. And then the product reaction solid is the oxide. In this case, we can have residual oxygen in the form of waste, which must be evacuated by the chamber. For example, low temperature deposition of silicon oxide at 450 Celsius. It starts from a compound of silicon and hydrogen. By using oxygen as secondary precursor, we can have the formation of silicon oxide in the solid form and hydrogen as residual waste to be evacuated. we can have also the possibility to think, even though this is the most common reaction that is used when we want to form silicon oxide, but in principle, we can have also dry oxidation, which happens with a rate which is sustainable from an engineering point of view at higher temperature, those here represented, in which we do have a solid silicon, which is going to react with oxygen to form solid silicon oxides. We can have a wet oxidation for the formation again of silicon oxide, not by using oxygen, but by using water vapor. And in this case, we have the formation of silicon oxide with the waste, which is again hydrogen. Or other possibilities is the formation by the same precursors made by silicon and hydrogen by using nitrogen oxide, and thus having as production results again a solid phase, which is our coating, and exhaust gases that in this case are nitrogen and hydrogen. Or compounds, like for example in the case of non-oxide, for the fabrication of silicon nitride, through what we have already defined, low plasma CVD techniques, by using hydrogen chloride silicon and by using ammonia in the gas form, thus forming the solid, and you see again thus having the result waste in the vapor phase as a gas phase, which must be evacuated like this one from the chamber in which the reaction is going to happen on the surface of the substrate we want to coat. Two are the phenomena which are going to control the deposits to be formed at high temperature. At high temperature, we have a potential limitation in terms of deposition rate due to mass transport. When we are going to think to low temperatures, we can have a deposit limitation, which is instead linked directly to the reaction rate. And if we want to give, let me say, power, we want to activate the reaction. As we know, as it happens in any chemical reaction, we need to overcome a minimal energy barrier. And so one possibility is that to give this energy by heating the substrate. And this means by heating also the surface of the substrate. And in this case, we have the case in which heat is used. But in some cases, or in many cases, that depends on the list of materials that we have in mind, in order to properly activate the chemical reaction, thus having a reaction rate, deposition rate, which can be considered satisfying by engineering point of view, we should reach too high temperatures, which could be not compatible, for example, with low melting point materials. And so we have one of the most common variant of the CVD technologies, which is the plasma enhanced chemical vapor deposition methods, in which we use a radio frequency induced plasma, as in the sputtering case. So we have ions, and these ions are going to transfer energy into the reactant gases, and thus allowing the possibility to the chemical reaction to happen, or also at lower temperature process, lower than 300 Celsius. And this, let me say, it's quite important, because if, as an example, you want to make some kind of coatings by using CVD techniques onto aluminum bulk materials, aluminum substrate, we know, just to give to you an example, that the melting point, the melting temperature of aluminum is quite low if compared with other metallic elements because it's around 660 Celsius, and thus, in order to avoid melting of aluminium or incipient melting on the surface of aluminium that we could need, for example, to reach the temperature requested for standard CVD techniques, if we use plasma enhanced CVD, thus we can maintain our substrate to a temperature value which is compatible with the melting temperature of the materials itself, and thus without any deterioration of the component of the materials to be coated. CVD processes are ideally suited for the deposition of thin layer of materials, as we have said, and as difference to some other deposition processes, because we do not have, like for example in the PVD, condensation, but we have gas which are absorbed on the surface and then that which gave rise to the chemical reactions. They are CVD layers, they are able to follow the contours of the substrate. And so they are conformal to the subset as shown below. And this means that this is less, with respect to PVD, line of sight technology, provided that the absorption of gases can be established also in area like holes or geometric shape discontinuity. And this is important for the performance of the process. But what we can say that there are some limitation, or if you want, disadvantages of CVD processes, generally speaking. First of all, because we could not have available any chemical reaction or any suitable chemical reaction to fabricate a certain type of coatings. In general, what we can say that they are, these kind of processes, they are not suitable to obtain mixture of materials as those we have just seen related to the PVD technologies. Then we do have problems related to safety. We just need to remember this, which is a very important issue, but in any case, we are able to manage it from an engineering point of view. And this is due to the, let me say, hazard characteristics of some reactants that can be used, for example, as ammonia, we have cited, or, for example, to hazard properties and characteristics of the waste phase, gas phase, which must be evacuated by the chamber, like, for example, just to give you another example, hydrogen chloride or hydrogen fluoride or chlorine itself. So what is not so, let me say, important, apart from safety, from a point of view regarding the wall equipment for PVD, is very important for CVD due to the presence of salty gases from the chemical reaction, which can be corrosive, which can be flammable, which can be pyrophoric, which can be very toxic for what it concerns the operator. So this is an issue so that we are able to manage, but which must not be neglected, must be remembered. Here, I prepare for you a very condensed table in which you have a sort of comparison of advantages or, if you want, disadvantages of thin film deposition technologies. And you see I have reported the thermal evaporation, the electron beam evaporation, and the sputtering for what it concerns the PVD process. processes, and plasma-enhanced CVD as well as low-pressure CVD system for what it concerns CVD. I have also reported that's not exclusively true, but is most common cases in industrial use of this kind of technology, which kind of materials are used for these processes. And as you can see here, CVD technologies, even though we can fabricate also carbides or whatever else you want having available a chemical reaction, but they are mainly used to fabricate dielectric coatings, that is, coatings which are very important for semiconductor or electronic, generally speaking, industries. As instead, for the PVD, they can allow to us to make fabrication of metal-based, non-oxide ceramic base, and also dielectric materials. And so they are more used in the industrial, let me say, instead of electrical engineering. But please remember again that we have, with respect to what we have seen for the thermal spray technologies, generally speaking, very, very low deposition rates, very low deposition rates. Generally speaking, thermal spray technologies, HVOF or plasma, they have different features, but just to give to you a rough number, they are able to spray kilogram per hour. Here we are talking about, in the best cases of CVD, PVD is lower, of deposition rates which are near, usually less, 1 micron per hour. And this concludes our discussion about surface engineering. Now, let me move to the next presentation, which is the last topic of our course. And, oh, sorry, I need to launch my presentation, okay. Okay, that's one, okay. We have said, talking about surface engineering, that this kind of techniques we have available, they are used in order to fabricate surfaces having, let me say, special properties. These special properties can be functional properties, as for example optical reflectance, or can be properties which are more near our concept of structural properties, like for example hardness, that is wear resistance, or in order to limit the interaction with the environment, that is to reduce eventual corrosion problem. And so this is for us, for our application, the main field. So we functionalize our surface, the surface of our component, essentially to have a better wear resistance, or generally tribological resistance of the components, or a better corrosion resistance of the components itself, having in mind the working environment, or in to some cases, to some extent, also better wear and corrosion resistance. So it's now the time to discuss a little bit better, respect what we have done some years ago, about corrosion and wear, which are the basic degradation phenomena for which surface engineering is able to give to us as engineer a very useful tool. Remember, in any case, as we have said many times, that the techniques to coat a component is not a technique free of cost. That is, that's an additional fabrication step which give more added value to our product, but which give also an additional cost to the fabrication cost of the component, and so they must be used where they are necessary, having in mind a cost to benefit ratio with respect to the expected lifetime of our component in real working condition. So let's start to discuss first about corrosion. As you perhaps should remember, but now we will be again into, let me say, the topic. When we talk about corrosion of materials, generally speaking, that is about interaction of the materials with the working environment, that's not always the case, but we can have a response which is of the component, a response of the materials, which is always linked to the surface properties, because our working environment is not, apart from the existence of defects, in contact with the inner of our component, but it is in contact with the surface of our component. And so let me say, the logical connection between the surface engineering technologies and the corrosion is fully existing, because eventual degradation phenomena due to corrosion are going to start and be, first of all, localized to the surface of our component. And when we talk about corrosion, we can also say degradation of the materials, that's the same. We need to divide the potential or the possible degradation phenomena into broad classes. The first one is the so-called classes of corrosion phenomena based on electrochemical corrosion. What is here very, let me say, strictly indicated with EC. The second class of corrosion phenomena are the phenomena which undergo under the definition of high temperature corrosion phenomena. And this kind of distinction is not, let me say, only a didactic distinction, but it is strictly related to the fact that the mechanism with which our materials, we should say better, with which the surface of our material is going to interact with the working environment, the mechanisms are different. When we do have electrochemical corrosion, we have exchanges of charges, ions and electrons, oxyreduction reactions, which need, in order to assure ion mobility, the presence of a condensed phase. So all the corrosion phenomena which are going to be present in the presence of a condensed phase when existing, based on exchange or movement of electrical charges, ions and electrons, and thus requesting or implying an oxyreduction chemical reaction, they are in the area of electrochemical corrosion. Atmospheric corrosion of materials is an electrochemical corrosion a phenomena, because you remember that our atmosphere, it has a relative humidity, that is, the condensed phase is going to be existing. When instead we have in a working environment in which we do not have any condensed phase, and this implies that ion movements is not allowed, the eventual reaction with the working environment is going to happen through direct chemical reactions. For example, with oxygen for oxidation, for example, with sulfur for sulfidation, and so on. And we do not have oxy-reduction reaction, but we have just chemical reaction. And this phenomena of deterioration of material surface composition, in this case, when we do not have a condensate phase, they belong to the high temperature corrosion area. For what it concerns the response, generally speaking, obviously the response, that is factors which are going to affect, generally speaking, corrosion behavior of materials, they depend on the environment, they depend on the material properties, they depend on the physical conditions in which our surfaces is going to work inside the working environment, like as well, for example, design, stress, external energy, and so on. So we have different contributions which can address our discussion about the corrosion behavior of a component of our materials. Somebody or sometime has said that the corrosion is a sort of return of the materials to the original state. If we think, for example, in the case of metallic alloys, we usually have we could say a sort of precursors of the metallic alloys, the original compounds, to be more precise, which are in our ore. Then we do have a refining process to technological processes with which we can, for example, fabricate from the initial stable oxidized state our desired alloy. When there is the reaction with the working environment, our refined metallic alloys, depending on the composition of the working environment, can come back or tend to come back to the original state. That's the only meaning of this, let me say, sentence, which can be easily found by reading the specialized test on corrosion. Let's start with the electrochemical corrosion. This will be our first discussion, and then we will move later on the high temperature corrosion, called also hot corrosion. They are synonymous. Well, we have said that we have an electrochemical reaction. At a qualitatively level, in this moment, when we talk about electrochemical corrosion, the forms of corrosion which can happen are usually divided into big areas. And so we can have the forms that are described here on these slides, which are different in terms of way to proceed onto the surface, and which are also different in terms of degree of severity, depending on the function for which the component has been designed. We can have the uniform corrosion, the uniform attack, which is not always the only form existing, in which we have reactions which are, let me say, more or less uniform all over the surface of our component. But we could have also other mechanisms, like, for example, selective leaching. If you have, for example, alloys, it could be happen, like in the case of copper zinc alloys, copper zinc express alloys, that in some cases not both the element zinc and copper are subjected to deterioration, that is to corrosion. But for example, one of them is very rapidly deteriorated. That's the case, for example, of the behavior of zinc. So in this case, selective leaching means that our starting alloys, our brass starting alloy, will lose progressively quantity of zinc, thus changing composition, thus changing properties with respect to the quantity, which is less, of copper, which is lost due to the corrosion phenomena. Then we can have also, for example, intergranular corrosion, which means for polycrystalline materials that we are thinking about a form of deterioration, of corrosion, which runs along grain boundaries. In some cases, this is possible due to the existence, for example, of spatial phases. And this means that the attacked zones are not all the grains of the materials like this one, but the deterioration, the attacked zone is going to have a preferential route, which is along grain boundaries. This is not a uniform attack because, as well as the selective leaching, because the attack is concentrated on the grain boundaries. We can have stress corrosion phenomena, which we will dedicate a slide, which is a sort of, let me say, combination of corrosion due to together with stress effects. We will see later on. But also in this case, we do not have any uniform attack. We can have galvanic corrosion. This kind of corrosion, which is very important, is going to happen when we put in contact two dissimilar metals or two dissimilar metallic alloys, and the meaning of similar, dissimilar will be clear to you later when we will talk about potential in electrochemical corrosion reactions. But just to give to you a definition, when you put two dissimilar metals in contact, for example, because they are physically or mechanically jointed, we can have just one of two is subjected to corrosion, whilst the other one results to be protected. Also, this is not a case of uniform attack. Erosion corrosion, that's another possibility. That is the synergic effect of erosion with breakdown, for example, of passivation layers by erosion and enhancement of deterioration by corrosion. We can have, still not being into the area of uniform attack, the pitting corrosion that we have mentioned, if you remember, for the passivating materials, especially, for example, for the stainless steel. If you remember, when we say that we have in front of us a stainless steel materials, this means that these materials, due to the presence of at least 12% of free chromium into the alloy, is able to form a very thin surface layer of chromium oxide, which, being a ceramic material, so now we can also underline or stress another concept, is able to avoid electrochemical corrosion. Which is the other concept before going on the pitting, is that when we talk about electrochemical corrosion, which is a list of phenomena due to the presence of oxy-reduction reaction and thus of electrical charges movement, obviously, if we are talking about ceramic materials, this is not possible. So electrochemical corrosion is very important for us for all materials having a suitable electrical conductivity. And this means that they are corrosion forms essentially for metals or metallic alloys, being polymeric-based materials as well as ceramic-based materials, not electrical conductivity materials. Coming back to the chromium oxide, this chromium oxide is thus able, being a ceramic material, to stop movement of electrical charges, and thus stop movement of ions and electrons, and thus prevent from the presence of electrochemical corrosion phenomena. But remember, for stainless steel, this chromium oxide can be attacked by quite a complicated mechanism, in which is not the case to go inside. Remember that the corrosion, let me say, issues are subject of a whole course, for example, in the degree of chemical engineering. So we are going to make a summary of the most important concept. I was telling to you, in some special cases, like for example, the presence in an environment in which we do have Cl minus ions, the passivation state can be attacked by a very special form of corrosion, which is pitting. Very small holes, which are going to destroy our passivation state, and which are not so influencing too much the thickness of the components because they are very, very small, but they can be very dangerous for us because we can remember that they are defects on the surface in which we can experience a high level of stress intensity factor. And so due to all what we have studied during the chapter of fracture mechanics, this must be avoided if the component must sustain loads. Another form of corrosion, of the most important, this categorization of corrosion form is something universally accepted for electrochemical corrosion phenomena, is crevice, which can happen between two pieces of the same materials, where we do have, for example, joints in which we do not have the same environment existing for the resting part of the material itself. It is also defined as corrosion under deposits, because under the deposits, and think, for example, to a pipe in which we have a fluid inside, under the deposit, the environment is different from those on the other part of our component where the fluid is running, and so is changing continuously. So when we talk about electrochemical corrosion, uniform attack, which is, let me say, something more near to our common feeling, is just one of the possible corrosion form, and we need to take in mind also the possibility of existence of other corrosion phenomenologies, always depending on electrochemical aspect, that is on oxy reduction reaction, but which are not categorized as a uniform consume of the materials itself. Pitting corrosion, okay, we have said that we can go on. You see, just to give to you some figures, these black holes, very small, sometimes pits are cannot be seen by visual inspection. They are very, very important and very dangerous for us. When we talk about components having structural functions. How can avoid pit? If we cannot modify the working environment, we need to use materials which can be passivated, and they exist, for example, titanium-based alloys, but materials for which the Cl minus ions are not able to attack the passivation state. That for titanium alloys, it's not chromium oxide, but is titanium oxide. So going on, very important, very interesting for us is the stress corrosion form, which was mentioned in the previous 8 form of basic corrosion, electrochemical corrosion phenomena. It is also called stress corrosion cracking. What is going to happen? It's going to happen that for certain, not for all, for certain combination materials working environment, and we are able to know which are these combinations because they are listed on specific manuals. If our component is subjected to a tensile stress, so we should need to have two factors: a materials environment couple, which is able to manifest the stress corrosion cracking, but we need also to have our component stressed in tensile. And here you have some examples which have been taken from a specific test. We can have intergranular propagation of a crack with a very sudden rupture of the materials itself, that is, of the component itself. There are two, let me say, concepts which must be kept in mind for this problem, which could be also very serious problems. First of all, we can ask to us if we need to take care of eventual stress corrosion phenomena when we do have a component into exercise which is subjected to tensile stresses. This is the first one. The second aspect is that the materials must work in an environment, and they are listed, for which the stress corrosion phenomena can happen. And so if the answer is yes to both these questions, we must remember that stress corrosion can happen, and we need to make something. One thing that we could do is to use, because it exists, a factor that is a stress intensity factor, which is called K1, like K1 we have defined in the fracture mechanics, but with the predix SCC, which stands for stress corrosion cracking. This is a figure, this is a number, which is usually given because it has the same meaning as unit measurements as K1C in megapascal per square meter, okay? And what is going to happen is that even though we have our system, which is subjected to tensile stress, our materials, which is going to work in an environment where stress corrosion cracking is happening, If the stress intensity factor K1 for our component is lower than K1 SCC, that is lower than the stress corrosion cracking K1, well, the stress corrosion phenomena is not going to happen. If K1 is higher than the critical value, in this case, our critical value is K1 SCC, well, then stress corrosion cracking can happen. So we have also the possibility, this is what I'm going to tell to you, to let our component work in an environment which is able to give potentially stress corrosion cracking if the stress intensity factor is lower than K1SCC. The possibility to use this design guideline in order to avoid stress corrosion cracking depends obviously on the absolute value of the K1SCC, because if this is very low, some units of megapascal per square meter, well, it cannot be used, because if it is too low, is as to say, well, in order to avoid stress corrosion cracking, let's keep our tensile stress to a very low value. And that's very, let me say, simple, but not usable in an engineering approach. So if the value of the K1SCC, it allows us to avoid stress corrosion cracking by taking the K1 value lower than K1SCC, that's fine. Otherwise, we need to change materials, or we need to modify our working environment for a given materials in order to avoid these very serious problems. Why we need to consider this when it exists? Because as the starting metallic alloys goes in a situation of high resistance materials, so I'm talking about high resistant metallic alloys, which are very important for the aerospace fields, generally speaking, the probability to meet stress corrosion damages are going to increase. So for high strength materials, we need every time to ask us if the materials with which we have done our component in that working environment, when they are subjected to tensile stresses, can undergo under stress corrosion phenomena. If the answer is yes, we have a look to K1SCC. If our K1 can be lower than K1SCC, we have resolved the problem. Otherwise, we need to change materials or modify the environment. Another form, very important for you, of, let me say, special electrochemical corrosion damage is what is going to happen for the aluminium alloys. Structural aluminium alloys is the so-called exfoliation corrosion phenomena. Well, also this is a very, very, let me say, particular, which can be easily contrasted if we remember which are the reasons because of this kind of phenomena can happen. First of all, it cannot happen for any kind of aluminium alloys, but it could happen for aluminium alloys which belong to the class of aluminium alloys for plastic deformation technologies in order to fabricate the final component. How can we see from this drawing that this is the case of aluminium alloys subjected to plastic deformation technologies? Because we have elongated, in this drawing, elongated grades. Then there is a second condition which must be met, is that the aluminium alloys, which can be used for plastic deformation technologies, must be treatable by a thermal point of view. That is, can be, must be, can be, as you want, hardened by precipitation. These restrict, for example, the area of potential exfoliation corrosion phenomena to aluminum alloys of the classes 2000s and 7000s. But if you remember, these are the two most important classes of aluminum alloys which are used for the cold part of an iframe in the aerospace industries. And why it is called aluminum exfoliation corrosion? Because due to the presence of elongated grains, the corrosion is going to happen on this red line that is along, again, the grain boundaries. And so there are thin sheets of materials we are going to be detached one from the other one. Well, why this happen? This happens for a very simple reasons, because of when we have made our thermal treatment in order to establish inside our aluminum alloys precipitates which are able to give to us the desired increase in yielding strength of the materials. The precipitation process has not resulted in a uniform distribution of precipitates inside the material itself, but precipitates are essentially concentrated along grain boundaries. When this is going to happen, well, then we can have exfoliation corrosion. But this situation in which the precipitates are not uniformly distributed inside the grades of the materials itself is not a good situation in terms of improvement of mechanical properties, yielding strength, for example, of the basic aluminum alloys, which is the reason because of we use precipitation hardening aluminum alloys. And this means when this is going to happen that we have made a wrong thermal treatment. So how to overcome, how to solve eventual corrosion phenomena due to exfoliation, which is a corrosion phenomena which can happen for aluminum alloys subjected to thermal treatment for hardening and to plastic deformation technological processes, just selecting and making the proper thermal treatment. The proper thermal treatment for a given aluminum alloy composition is known in all the parameters. This means that we do not have to use different parameters of the thermal treatment, otherwise we could have anomalous precipitation of the compounds and we could enter into the corrosion exfoliation degradation. So quite easily to be solved this kind of corrosion, just make the right thermal treatment to increase extrinsic mechanical properties of the base aluminum alloys. Now, when we study the corrosion phenomena, essentially we have, and this applies also for the high temperature corrosion. So I'm just telling to you an introduction concept, which then must be specialized depending on the class of the corrosion itself, but which can be applicable to both of them, is that we have chemical reaction. We can have direct chemical reaction like in high temperature, or we can have electrochemical based reaction like in electrochemical based corrosion phenomena. But we do have chemical reaction, and anytime we do have chemical reactions, we can study, let me say, our problem by following two different approaches. One approach is the thermodynamic approach, and the second one is the kinetic approach. Which is the difference between them? Well, the thermodynamics approach is something which is able, basing on the thermodynamics of chemical reaction, that is, for example, the Gibbs function, is able to tell us if a certain chemical reaction can happen or not. So thermodynamics says to us, gives to us the answer that reaction can happen or that reaction cannot happen. When the answer from thermodynamics is that any reaction cannot happen, well, we have finished in the sense that we can say that chemical reaction, which is a degradation reaction, is not possible. And so, if that chemical reaction would be the corrosion reaction, we can say corrosion is not going to be present. But the problems for us as engineers arise when the thermodynamics tell to us, yes, that reaction, that is that chemical reaction, that is that corrosion reaction can happen. Because as you can understand, it's quite different the case in which the chemical reaction, when happens, is very fast, or a chemical reaction, when happens, is very slow. Because we are dealing with components. So for each component, we have a design lifetime. And this means that we need, when the thermodynamics tell to us that a chemical reaction can happen, we need, as engineer, we need figures which tell to us how fast is that chemical reaction. So we need to go into the corrosion rate, we need to go into the kinetics of the corrosion phenomena. We could also discover, generally speaking, that a chemical reaction can happen, but it is being so slow from a kinetic point of view, if compared with the expected lifetime of our component, we could also, let me say, generally speaking, I underline again, say, well, corrosion can happen, but it is so slow, so it can be tolerated by our component. And so we need to know both elements of thermodynamics and elements of kinetics of corrosion phenomena. Now we specialize our discussion again for electrochemical. And as you can see here, we are talking about corrosion in presence of condensed phases, since I have written corrosion in aqueous solutions. If we make our initial approach in terms of thermodynamics of corrosion, first of all, we need to say that they must be present for, and this is also called the final four of corrosion, fundamental parameters at the same time, in order to let the corrosion phenomena, electrochemical, possible to happen. We need two electrodes, then we will specialize that. One is an anode, the other one is the cathode. Let's just say at the beginning that what is going to be corroded, what is going to be consumed during the electrochemical reaction is the anode. Then we need a ionic circuit, and we need also an electrical circuit. So we need two electrodes and two circuits, one for which ions, and for this we need a condensed phase, can move. Another one instead in which electron can move, and for this we need materials having a metallic behavior. If we eliminate one of these final four parameters, this is able to stop the corrosion phenomena. The anode, according to the definition which is used in the corrosion theory is the part of the metallic surface which is corroding. That is, it can be also oxidized, but it is corroding. That is the part of the surface from which ions leaves the metal to enter the electrolyte, that is the condensate phase. And this, for example, means that if we think to something which is made of iron, let's talk about pure iron, just to have a fixed point, then we need to the anode, if iron is being corroded, that ion of iron, like for example in the forms of Fe++, leave the surface of our metallic iron-based materials and enter the electrolyte. This means that our iron element, from the initial state of 0 as oxidation number, they are going to move to +2 oxidation number. And so this is an oxidation reaction in which we have an increase of oxidation number, and at the same time, since we need to maintain the electrical neutrality, we have, in this case, as an example, 2 electrons which are left. These electrons, which are left, they must be put in circle in the electric circuit, and they must reach the cathode of this chemical reaction, which is a material, can be also a metal surface, but let's say in general is a materials, in which these electrons, which are released from ions, positive ions, left by the ions which leave the metallic surface, in which these electrons are consumed. For example, because they go in contact with hydrogen ions. So one hydrogen ions can consume 1 electron and become hydrogen, H. 2 hydrogen together can bond and form hydrogen in the form of a gas. And if we put, as an example, our attention on hydrogen, the question could be, where hydrogen are coming from? They can come from the composition of the electrolytes. For example, in the case in the electrolytes, we do have an acid substance inside. But please remember that any condensed solution, it has a pH value. That's for chemistry. So it has quantities depending on the pH values of ions H plus and of ions OH minus. So in condensed solutions, we have hydrogen ions. And in this case, if we put our attention on hydrogen, we can see that hydrogen, in terms of oxidation number, is going to pass from the oxidized state +1 to the reduced state 0 when it is linked in the form of H2. And so at the anode, we have the oxidation reaction, which is the corrosion reaction. At the cathode, we do have the reduction reaction, and thus we do have, in electrochemical-based corrosion, oxy-reduction reactions. This will not be the case of high-temperature corrosion, but it is essential, and it must exist on the basis of the final 4 that we have just mentioned for the electrochemical corrosion. And so you see, we have satisfied all these 4 conditions. The anode, that is a material which is going to lose ions and leave electron free, the cathode in which the electrons are consumed, the ionic circuit, that is ions coming from anode, which are going to go into the electrolyte, and the electrical circuit, which is able to put the electron on the cathode in contact with species which are able to consume the electron itself. And so the basic corrosion cell, for what it concerns the electrochemical corrosion, is what is reported here. We have a metal piece, for example, the anode, for which we have ions which are going to go into the electrolytes, what is called here M+, leaving electron. This electron, being existing an electrical connection between the anode and the cathode, can go onto the cathode where they can match, they can be in contact with species which are able, this is another case, the OH minus, able to consume the electron, and thus the basic corrosion cells is composed of the four elements we have defined. And what we could say before going inside, let me say, yes, the theories of the corrosion thermodynamics, which is based on the Gibbs free energy, but we will start this on the next lecture on Wednesday. We can say that it is not possible to think about the possibility that we do have just the release of ions, because that's not possible. To have a release of ions, we need to have a release also of electrons. And this means that the overall system cannot be charged. All the electrons which are left by the ions which are going to go in the solution must be consumed. And so if we are able, for example, to contrast the consume of the electron, the rate of the consume of the electron, as well as if we would be able to contrast the amount of ions which are going into the electrolyte, we do have a tool in order to reduce the corrosion rate, because the quantity of charges must be always the same. We do have a sort of two currents, one positive due to the ions and one negative due to the electrons. These two currents must be equal. This mechanism, as to be clear again, cannot happen in materials which are not able to let electron flow inside them, because this cannot this will suppress the mechanism for which electrons are consumed. And this is the reason, because we have said that this kind of corrosion, the electrochemical, is essentially existent only when the environment is aggressive for metallic-based materials, because both in polymeric-based materials and in ceramic-based materials, the possibility to have current intensity that is flowing of electrons is not possible. So I think that for today it's all. So we can start and then complete in the next lecture some remind about the Gibbs free energy equations and the next equations, that is the basic tools that are used for the electrochemical corrosion phenomena in terms of analysis of thermodynamics of the corrosion phenomena itself. For today it's all. So if you have any questions, please ask to me. I would like to ask if Cimaglia Maria Ludovica is present. It's not present? Okay, so I will write to her a mail, because she the only students which has booked the presence on next Friday, and so I will write a mail to her just to advise that Friday there is no lecture. Any questions? Okay, if not the case, we will meet again next Wednesday. Good afternoon to everybody.